Hello and welcome back. This video will be on section 3.3, where we are looking at data values and being able to describe their position within a set of data. So the first way of describing the position of a data point is going to be using the z-score. And this is a measure of how far away a data point is from the mean. So if a data point is really big and it's a lot bigger than the mean, we'll have a large data value. If we're very close to the mean, we'll have a large z value. If we're really close to the mean, we'll have a very small z-score. So z is just going to measure how far away we are from the mean. And I think the best way to introduce the definition is with an example. So let's say that we're looking at U.S. male height, and the mean value is going to be about 70 inches, and the standard deviation in male height in the U.S. is going to be about 3 inches. So someone who is 73 inches tall, about 6'1", is going to be 1 standard deviation above the mean. So 1 standard deviation, we're going to just turn this into a number, and that z-score is just going to be 1. So if we come back and look at our formula right here, and we're working with a population, all of the U.S. males, it's not going to be a sample. Our male is going to be 73 inches tall, and what we're going to do is we're going to look at how far away 73 is from 70, but we're going to normalize with respect to the standard deviation. So all this means is that 73 is going to be 3 inches more than 70, but 3 inches is exactly 1 standard deviation. So the z-score is going to be just how many standard deviations we are away from the mean. Looking at another example, so say someone who is 60 inches tall, so exactly 5 foot tall, 60 minus the mean divided by our standard deviation. 60 is going to be 10 inches below the mean. So 10 inches below, meaning we're going to be subtracting, so this is negative 10, but we're still going to normalize with respect to the standard deviation. So when we divide this out, we're going to get negative 3 1/3, which we round z-scores to do 2 decimal places. 2 decimal places. So technically I could write 1.00, but I think it's clear from the context. So here we'll round 2 decimal places. So this z-score is negative 3.33. Meaning that 60 inches is going to be about a little over 3 standard deviations away from the mean. And again, the formula, both of the formulas are exactly the same. It's just whether or not we're working with a sample or a population. In either case, we take the data point minus the mean to see how far away we are, and we're going to divide by the standard deviation. So a little bit more about z-scores. So again, like I said, z-scores are just how many standard deviations away a value is from the mean. And z-scores are interesting because they have no units. I've normally been talking about, say, a z-score of 1 means we're 1 standard deviation away from the mean, in fact, above the mean. But the z-score itself, 1, will have no units. The units will cancel from the top and the bottom, and you're left with nothing. 2 standard deviations is where we sort of define significance. So if you were below 2 standard deviations below the mean, or if you're above 2 standard deviations above the mean, this is called a statistically significant event. So z-scores that are less than negative 2 or bigger than 2 are called significant. So if we have our range of z-scores right in the middle at 0, this is when a value is exactly equal to the mean, and then we can have z-scores that are both positive and negative. anything bigger than 2 and anything less than -2 is considered a significant event. So this is significantly low or significantly high. And like I just mentioned, if you have a positive z-score, this means above the mean, and negative z-scores mean below the mean. So let's quickly look at another example. So back to IQs. An IQ will have a mean of 100 points, and the standard deviation is going to be 15 points. So the IQ with a score of 2, with a z-score of 2, is going to be 130. And why is this? Well, this is positive 2, so it means we're going to take the mean and we're going to add 2 standard deviations to it. So one standard deviation is 15, so after we add 2 standard deviations, we're up to 130. So 130 is 2 standard deviations above. Whereas the IQ with -2, with a z-score of -2, is going to be 70, because if we go to the mean and we go down 2 standard deviations, we hit 70. So 70 is exactly 2 standard deviations below the mean, which is indicated because we have a negative z-score. The last thing that we'll look at in this video are percentiles. So a percentile is again going to be a way to distinguish where a data point is amongst the rest of the data. And the kth percentile is going to be the value that's bigger than k% of the data. So if we have all the data and we've arranged it from smallest to largest, the kth percentile, pk, is going to be greater than k% of the data. The rest of the data will be bigger than pk. This is relatively easy to calculate when you're given a set of values and let's say in this situation we want to find which percentile 4 corresponds to. So 4 is greater than 2 numbers. It's greater than 1 and it's greater than 3. So within this data set, 4 is greater than 2 out of the 10 total values. So 4 is greater than 20% of the data. This means that 4 is the 20th percentile. And then using our notation, this means that 4 is in fact P20. Okay. So again, to calculate the percentile corresponding to a particular data value, you just count how many data values are below. To do this, we'll need to arrange the data in order, and then we'll notice, 4 is greater than 2 data values. So 4 is greater than 2 out of the 10 data values, and 2 out of 10 is 20%. What's maybe a little bit more frustrating is turning a percentile into the data value. So in this case, it was easy to take 4 and to turn it into a percentile. It's harder to go the other way. And in fact, there is no universally recognized, universally accepted way of doing this. Different mathematicians may do this in different ways. So we will adopt one way in this textbook, but just be warned that this may mean something different to someone outside of this class. So let's look at this process. So we're given a data set and we want to find pk. So we're told that we want to find a kth percentile, and we have n data values in the set. In our previous set we had 10 values, but there could be a lot more. We could have, say, like thousands or if not millions of data values in the set, and we want to find the kth percentile. So when I say the kth percentile, we mean we want to find the number that's greater than k% of the data. So the first step is figuring out, well, how many data points would make up k% of the data. So this L here corresponds to how much is k percent of the data? So we'll just take k percent of n, which is just this formula here. We turn k percent into a decimal by dividing by 100. And there are two situations. Either L is not a whole number, or it is a whole number. And there's a different process in both of these. So I want to start over here in the situation where this L is exactly a whole number. So I'll come back to this in a second. So here's the data set that we saw before. And what we want to do is find P50. So P50 is, again, it should be greater than 50% of the data. So that should ring a bell. We want to split the data in half. So this is pretty much exactly like the median. The median will divide the data set in exactly half. So let's find P50. So 50 here will correspond to 50%, and there are 10 data values. So n is going to be 10, k is going to be 50, and L is going to be 50% of 10. 50% corresponds to 50 divided by 100 times 10. This is 5. So this is a whole number, which means that I have to follow these instructions. So pk is going to be the number halfway between L, which in this case is 5, and the L plus 1th number. So the fifth number, so the fifth data value is 1, 2, 3, 4, 5. It's 12. The sixth value is going to be 16. So P50 is going to be halfway between 12 and 16. So we can see that 14 will be the number right in between. The formula for this, the formula for the number exactly in the middle of two numbers, we'll add them together and divide by 2. So 12 and 16 is 28. 28 divided by 2 is 14. So P50 is 14. And this is exactly the same number that we would get for the median. We have an even number of data points, so the median is going to be halfway between the middle two. So we know how to deal with L when it's a whole number. When L is a whole number, we look between L and L plus 1, and we take the number halfway between. It's a lot easier when L is not a whole number. If L is not a whole number, we just round up, and we take that term in the list. So let's do this for P25. So again, N here, we have 10 data values. K, we're looking for 25. So this means that we're looking for the 25th percentile. So we're looking for the number that's greater than 25% of the data. But how much is 25% of 10? Well, this is going to be L. So 25%, 25 divided by 100 times 10. This is 2.5. This is not a whole number. I can't find the 2.5 number in this list. There's a first number, second number, third number, fourth number, and so on. But there's no 2.5 number. That doesn't really make sense. So what we do is we round up. L rounded up is 3. So the third number, so the third value is 4. So P25, the 25th percentile, is exactly 4. Now, this may strike you as odd. P25 is 4, but before, when we calculated the percentile for 4, we said that 4 was the 20th percentile. And this is where things get a little bit murky, but essentially, 4 is bigger than 20% of the data. 10 is bigger than 30% of the data. So we can talk about P20 and P30. P of anything in between, we'll just stick with the smaller number. So 4 will be P20 and P25.